A warm and pleasant greetings to all. It gives me an immense pleasure to welcome you all for the first day, third session of National Conference on Analysis and its Applications, focused on fixed point theorem. A good teacher can inspire hope, ignite the imagination, and instill a love of learning. With these warm words, I am glad to introduce our eminent speaker of this day of this session, Dr. Aarti Saxena, Assistant Professor, Department of Mathematics, Manav Rachna International Institute of Research and Studies, New Delhi. She has completed her post-graduation in mathematics with specialization in computer applications at Bagh Educational Institute, Agra, and her doctorate on mathematical modeling of mucus transport in human lungs, normal diseased conditions from DEI, Dialbag, Agra. She has 14 years of teaching experience in various reputed institutions. Her field of specialization includes machine learning, statistical analysis of big data, mathematical modeling. She has completed 4 MOOC courses, 6 Coursera courses in both mathematics and computer-based subjects, coding, assignment, and work experience courses. In addition, ma'am has completed software engineering project on hotel information in DEI Agra. She has vast exposure in computer programming languages, operating systems. She has received meritorious awards in teaching and research. Ma'am has contributed tremendously to academics in various fields. She was an organizing member in many workshops, training programs. To her credentials, she has published more than 10 research articles in both national and international reputed journals. At present, she is guiding 3 research scholars. She is a prestigious author for many research books, to mention a few: Mucus Transport in Lungs, Effect of Sleep Intrinsic, Fuzzy Sets in Medical Decision-Making Process, and as a chapter, Kernel-Based Machine Learning Techniques, Big Data Management and Internet of Things for Improved Health Systems. With this, on behalf of Department of Mathematics, DG Vaishnav College, it gives immense pleasure to welcome our speaker, Dr. Aarti Saxena, to enlighten us today by her talk on Banach fixed point theorem and applications, with her extensive knowledge that she has on this topic. I hand over the session to you, to our speaker. The session is yours, ma'am.
Thank you. Thank you very much, Professor Usha, and warm welcome. I would like to first off my camera because of this camera I may face some issue, network issue. So sorry for that. And now with this, I want to start my talk. A very good evening to all the dignitaries, all the students, research scholars who all are present here in this session. I would like to thank Dr. S. Santosh Babu, Principal, Trinity College, Professor R. Ramanan sir, the owner and head of the department, for giving me this opportunity to share my views and my knowledge on fixed point theory. Uh, as Professor Usha introduced myself, Aarti Saxena, I am from Manav Rachna, in front of you discussing today the applications of Banach fixed point theorem. The flow of today's talk, I hope I am clear to all of you. Am I audible? Okay. Okay. So, flow of today's will be like we will
Hello, ma'am.
fixed point theory, which all of you know as
Aarti,
the
ma'am.
conference is focused on this topic about fixed point theorem. So after that I will give you a basic knowledge of machine learning, which I hope you have not heard since morning. And this is just to give you a flavor of this topic which discussed today, and so that you can join the streamlined flow of my topic, and that is the application of fixed point theory in so let us start the talk. So to all of you. So let us first start since we are talking about functional analysis. Let us first you all know basically you all know the so metric maybe any it may find in layman terms we can say that the metric distance it may be defined as Euclidean distance. Okay, so we have metric space. We must be four properties. Excuse me, a lot of disturbance is coming. Excuse me, a lot of disturbance is coming. Okay, so we will be discussing about the metric space property. The very first property is identity. In layman terms, I will tell you all the things today. So identity means if we will measure the distance of any point x from this space with itself, then it will be zero. And another second property is non-negativity property, which states that the distance between any two points will always be more than z plus zero, whenever we. And third property says use distance between element is the same as if we calculate the distance between y and x. And fourth one is the triangle inequality, which states that the direct distance between two points will always be less than if we will be taking the distances via any other point. So these are the properties of metric space which you all are aware of. Then we will be discussing Cauchy sequence. All these are the terms which we will be using in our theorem. So what is a Cauchy sequence? Cauchy sequence, as mathematical point of view, you can read about. But I'll tell you layman definition. In layman terms, we can say that a particular sequence will be a Cauchy sequence if the metric defined between any two elements of the sequence is always less than a very small number epsilon. Here A and B denotes the indices of the elements. So AB should belong to N, and N is the set of integer. So any two elements can be considered, and the distance between any of the two elements of a sequence, if it is less than a small number, then the sequence is said to be a Cauchy sequence. And then here is a point. What is a fixed point? So as far as the definition of fixed point is considered, a point is said to be a fixed point if under a map f of x is equal to x. So this is the basic definition. If in layman terms, let's suppose you are not a mathematician and I want to explain you what is a fixed point. So what is a fixed point? Fixed point is a point that doesn't change. Fixed point is a point that doesn't change whenever we change Am I audible? Sir, am I audible?
Yes, ma'am, you're audible, ma'am. You can proceed. But your screen is not visible, ma'am.
Am I audible, sir?
Yes, ma'am, you're audible, ma'am. Ma'am, but you have to share your screen.
Share a screen. Go to that PPT.
Is my screen visible? Is my screen visible to you all? Hello? Is my screen visible to all of you?
Yes, ma'am, it's clear now.
Hello, sir. Shall we proceed?
Yes, ma'am, you can proceed, ma'am. Yes, ma'am, you can proceed.
Okay. So, okay, fine. So, is it audible clearly?
Yes, ma'am. It's audible
Okay, thank
as
you.
well as.
So, I'm starting.
Ah,
Yes, sir. I'm starting with the very first slide again.
okay,
Shall I?
ma'am. You can proceed, ma'am. Yes, ma'am, you can
Okay,
proceed.
okay. Thank you so much. So
Thank you.
the flow of my talk will be, we will discuss first the basics of fixed point theory, and then I will do a flavor of so that you can get topics I want to discuss today. Application part of Banach fixed point theory, basically reinforcement. To discuss this topic, let's know a little about machine learning. So the flow will be like basics of point and then basics of machine learning, and then we want the application part. So here are a few basic points of when we talk about the fixed point, we talk about what metric space, Cauchy sequence, what the complete metric space. So in layman terms, the mathematical definition is here in front of you. If I want to explain you what is a metric space in layman terms, then what is it? For a metric space, you must have a set together with a metric defined on the set. Suppose we have a set X and D is the metric. The metric must satisfy the following four properties on the elements of a set X. So the very first property, accordingly, it says that it should be identified. Means the distance between any between the element and itself should be means the distance of an element from itself is 0. So this is the very first property of a metric space. Of a according to the second property, it should satisfy non-negativity restriction, which says the distance between any two particles, any two elements of the set will always be greater than 0. Because if it is 0, then y is not the another point, it is the same point as x. And that is the first point of properties. And then we have symmetry. This distance between x and y will always be same as the distance between y and x. And according to first property, triangular inequality should be satisfied. This means the distance between any two points will always be less than or equal to the distance which is measured via another point. So if a metric D satisfies these four properties, then on a set X, on the element of a set X, then the set together with the metric is said to be a metric space. Yes, sir?
Excuse me, ma'am.
Yes, sir.
Ma'am, some kind of disturbance we are hearing from your side, ma'am. Because your voice is
You're
breaking.
getting disturbance.
Yes, ma'am. Your voice is breaking.
So that may be internet issue now. Should I speak a little slow?
Yes, ma'am. Better, ma'am.
Okay, fine. Okay, fine. So next is a Cauchy sequence. A sequence is Cauchy if the distance between any two elements of the sequence is less than a very small number epsilon, which is a positive real number, then the sequence is said to be a Cauchy sequence. Next, we have a fixed point. What is a fixed point? Fixed point, as you have heard about, that if f is a map from x to x, then fixed point means f of x is equal to x, then x is said to be a fixed point. So it can be understood in many other ways too. Like a fixed point in layman terms, a fixed point is one which remains the same, which remains invariant under any map. F may be any map and it remains the same. Or we can talk about a fixed point like f of x minus x is equal to 0. The roots of this equation will give you a fixed point. Another definition is if y is x and y is equal to x, fx is here in front of you, you can see, and y equal to x is a line. So the point where this curve fx and the line intersect, that point is known as a fixed point. So it depends upon the understanding of the listeners in what sense you want to understand this fixed point and apply this fixed point, use this fixed point. It depends upon the understanding of listeners. The conclusion of all these definition is same. A fixed point is a point which remains invariant under any map. This F may be any map. Now here are few mappings. Since I'm saying F is any map, so there are types of mappings which I'm discussing. In the first one is Lipschitz. If L is a non-zero constant number, which belongs to a half closed and half open interval, then it becomes contraction. Why it becomes contraction? You all know, if we will multiply any large number with a number which lies between 0 to 1, then the resultant number will become obviously less than 1. That is why this definition of contraction means that the distance between the images is always less than the distance between the elements in the domain. So this means we are defining a contraction, and the map will become non-expansive if the distance between images and images is the same. This means the value of L should be 1. And similarly for isometry, the distance should be same for between images and between pre-images. So these are few mappings you can use. And as far as literature is concerned, we have seen these are the fundamental fixed point theorems, which one on the other hand states the same thing like Banach and Brouwer states that for any continuous map from closed disk to itself, there is at least one fixed point. What Banach says, if the metric space is complete, then there exists a contraction. So similarly, Cannon, Chatterjee, etc., they give so many fundamental fixed point theorems which you will be working on in your projects. So next is complete metric space. So as you all know that a convergent sequence is always a Cauchy sequence. Is it? A convergent sequence is always a Cauchy sequence. But if a Cauchy sequence becomes convergent, if a Cauchy sequence becomes convergent at a point lies in the same set, then we say that the metric space is complete. Okay. So next is Banach fixed point theorem. Here is the mathematical formulation of mathematical framework of Banach, and here I am telling you this in layman term. Informally, I am giving you this definition because this definition is the heart and soul of our proof in the application part. So I am giving you informal definition also for Banach fixed point theorem. You can think of this theorem like for a complete metric space, the application of a contractor on the elements of the set again and again. As I told you, if a number is less than 1 and you are applying that number, multiplying that number with any large number, obviously you will get a number less than 1. So that is the base of this theorem. That is, they are saying this theorem says for a complete case, the application of contractor on the elements of it again and again would eventually get us to an optimal unique value, and that is known, that optimal unique value is known as the fixed point.
Excuse me, ma'am.
So what we get from here is
Excuse me, ma'am.
Yes.
Ma'am, your voice is not clear, ma'am.
Voice is not clear.
Yes, ma'am.
Let me try from another device. Give me 2 minutes. Am I audible?
Not clear, ma'am. Still not clear, ma'am.
Am I audible now?
No, ma'am. Screen is not visible, ma'am.
Is my screen visible? Am I audible?
Now you can share the screen, ma'am.
I'm sharing my screen. Is it visible? Is my screen visible?
Yes, ma'am. Screen is visible, ma'am. Screen is visible, ma'am.
Shall I proceed?
Yes, ma'am. But your voice is not clear, ma'am.
Shall
The
I
screen is
proceed?
visible, ma'am, but your voice is not clear, ma'am. Ma'am? Now screen is not visible, ma'am. Now screen is not visible, ma'am. Ma'am, now your screen is not visible, ma'am. Am I audible to you, ma'am? Now it's visible, ma'am. Yes, ma'am. Yes, ma'am. Ma'am, excuse me, ma'am. Please unmute your audio, ma'am. Please unmute your audio, ma'am. Yes, ma'am. Yes, ma'am. Now you can proceed, ma'am. Ma'am, your voice is not audible. Voice capable. Ma'am, the network issue. Ma'am, ma'am. Yes, ma'am. You can proceed, ma'am. Voice is not here, ma'am. Add now screen with relay. Excuse me, ma'am. Excuse me, ma'am. Excuse me, ma'am. Ma'am, now you can start, ma'am. But all voice is not audible, ma'am. Still voice is not audible, ma'am. Excuse me, ma'am.
Is it audible?
Ah, yes, ma'am. Now it's audible, ma'am. But it's please unmute, ma'am. Unmute your audio, ma'am.
Is it audible?
Ah, yes, ma'am.
Chat is that?
Yes, ma'am. Screen is visible, ma'am.
Okay, so now I will talk about the application part.
Ma'am,
So,
please unmute audio in one device, ma'am. Then only it will be clear, ma'am. Now voice is not audible, ma'am.
application of fixed point theory.
Okay.
Audible now?
Yes, ma'am.
Okay. So, let me give you a flavor of machine learning. So, what a machine learning is? Is there anyone to talk about machine learning? Any one of you? Okay, so let me introduce this topic to you. What a machine learning is, let's suppose you are going for, actually not going, virtually you are on in a window shopping. I hope I am audible to all of you. So if you are purchasing anything for the first time, then you will not see anything in the recommending list. But if you will again join the same site for a second time, then you will definitely be able to see a list, a window which says that
Excuse me, ma'am. Ma'am. Excuse me, ma'am. Excuse me, ma'am.
जी मैम.
Ma'am.
हाँ जी मैम. उषा मैम, am I audible?
No, ma'am. Not audible, ma'am. Ma'am, excuse me, ma'am.
Usha ma'am, am I audible?
No, ma'am. Ma'am, please you stop sharing the screen, ma'am. We will share the screen, ma'am. And then you can talk through your laptop, ma'am. Excuse me, ma'am. Am I audible to you, ma'am? Ma'am?
Shall we proceed? Hello?
Ma'am, excuse me, ma'am. Please unmute your video, ma'am. Yes,
Am I audible?
Yes, ma'am. It's audible, ma'am.
Or is it audible? Usha ma'am, voice is audible?
Yes, ma'am. It's not audible, ma'am.
Okay.
It's not clear.
Let me start करूँ? So these are the basic definitions. This we are done with. Next. Okay, ma'am. Done. Please forward. Okay, fine. This is done. So here, please stop. So if we will see that what is a predictive modeling, back. Okay. So predictive modeling is to predict. Predictive modeling is to predict the future information using the historical data. So what we are doing basically in machine learning is we are using the previous historical data and we are giving the predictions about the future. So here are two types of tasks in machine learning. One is classification and another is regression. So if we have to predict the label, like whether a particular person has this kind of cancer or not, so that is known as a prediction classification task. And if we have to find out like the quantity, like we have to find the price of a house, then it is known as a regression type of problem. So machine learning basically is the field of predictive modeling and is primarily concerned with minimizing the error of a model or making the most accurate predictions which are possible at the expense of explainability. So next slide, please. Ma'am, next slide. Okay, thank you. So if we will talk about machine learning, then we need to know what is a supervised learning. Supervised learning means we have a predefined set of training examples with us, and using those examples, we are creating a model, and then we will give certain new data to the model. We will input certain new data, and based on the previous data entered, the model will give you the predictions about the new data, the results related to new data. So in supervised learning, this type of problems we used to discuss. It is therefore uses patterns to predict label values on additional unlabeled data sets. Unlabeled data is the data which we are entering into it, and historical data is the labeled data which is already there. So for example, it may use historical stock market information to anticipate upcoming fluctuations, or be employed to filter out the spam email. So such type of problems are known as supervised learning problems. In supervised learning, one more example is tagged photos of dogs can be used to identify whether the particular input data is belongs to which category of dog. So this is the most common example of supervised learning. And here is unsupervised learning problem. So what is that? As the name suggests, there is no historical data available. So the program is given a bunch of data which is unknown to us, the patterns, the relationships. There is no pattern, no relationship which is known to us. So what a program has to do, it has to find the particular relationships between the commodities, the heterogeneous clusters or the homogeneous clusters. It has to make from the entered data. As unlabeled data are more abundant than labeled data, so machine learning methods that facilitate this unsupervised learning, these are particularly valuable than the supervised learning problem. Next slide, please. Next slide, please. Next. Ma'am, please, next slide. Okay, so for example, in unsupervised learning, we may be calculating the fraudulent credit card purchases. So this is an unsupervised learning problem. Or the recommender system, which I talk about during window shopping on virtual basis. So this is also an unsupervised learning problem. Thank you. Next slide, please. Next slide. So here is the application part of fixed point theorem. So what a fixed point theorem is? Fixed point theorem says if there is a contraction mapping, then definitely there exists a point which is called the optimal value, optimal policy, and this is the fixed point of theorem. So fixed point of mapping. So to discuss this application part, we must know what is a reinforcement learning. Reinforcement learning, I explain with the help of an example. Let us suppose I want to learn riding of a bicycle, and I'm trying first time, so I fell down. I'm trying second time, I fell down. I'm trying third time, fourth time, fifth time. So based on my experiences, one day will come. It may be 500th trial on which I will get to know how to ride a bicycle. So based on
on my experience itself. I learned from what? I learned from whom? No one. I learned basically from my experience. So reinforcement learning is what I just told you, is learning by interacting with the environment. So this bicycle riding example is the most common example while explaining reinforcement learning. This is also known as trial and error learning and error learning. You are trying, you are making errors, you are again trying, you are again making errors. So every time you need to optimize your policy you are using. You need to optimize, you need to find the better policy than the last one when you are failing, when you are making errors. So these best policies are formed by your own experiences. So the best studied case in RL can be formulated as the Markov decision problem. So what a Markov decision problem is? Markov decision, it is basically a mathematical representation. It is basically a mathematical representation of complex decision-making processes. So what it does is, it is a discrete time stochastic control process. So when the term stochastic comes, this means, when the term stochastic comes, this means we are talking about randomness. So it is basically a random process. Okay, so if you have any kind of problem which comes under reinforcement learning, and you can formulate that problem into Markov decision process, then here is the Bellman optimality equation which comes under the same. So this is for Markov decision processes. Here R stands for the rewards. Rewards means the success. I'm getting success in riding bicycle. So that R is the reward. We want to maximize the reward, where P is the transition probability matrix. We are taking a transition from state S to S dash, from first trial to second trial. So this is the probability of going from one state to another, and V is the solution. Next slide, please. So this is the Bellman optimality equation which we need to discuss now. So next slide, please. Next slide. Okay, so here you can see the value function Vs. We define the value function Vs. We have defined a Bellman operator B. So what it is doing, it is again and again using this value function on the previous stage. S dash is the previous state. So this is an iterative procedure. This is using the previous state value to calculate the new state value. So in this way, you will see that you will get a sequence of value functions. So when you get a sequence, that sequence should be Cauchy. If that sequence is Cauchy, then it will itself converge. Why will it converge? Because we are defining a metric space on the set X. What is this X? Here, value function belongs to the set of real numbers. The X in the bottom here, the second row, shows the set for the complete value function, while the one at the top shows the set of values of a single state. So what we are doing, we are defining value function on the set of real numbers. And to define a metric space, what next we want is metric. So metric which we are taking into account is L infinity. And we all know that by functional analysis, R with L infinity is a complete metric space. So by using this B Bellman operator, if this operator becomes a contract, then that is we can easily is a contraction, and we will get a fixed point. Next slide, please.
Excuse me, ma'am.
Next slide, please. Next slide.
Excuse me, ma'am.
Next slide. Next. So here gamma is a number which is 0, 1, and we here contract.
Excuse me, ma'am.
Next slide, please.
Ma'am.
Next slide. Okay, it is not.
Excuse me.
Now means infinity now defined on R means complete R with L infinity becomes a complete metric space. And in the next slide, we proved that B is a contractor. So now B is a contractor. This means the sequence is Cauchy and every Cauchy sequence is converted in a complete metric space. Hence, this sequence will converge. So this means by applying this Bellman operator again and again on the value function, there will arrive a stage where we will get the optimal policy. And this is what the aim of our sequence. But here is a question. So till now, what we proved? We proved that for any finite Markov decision problem, there exists an optimal policy such that it is better than the previous one. And now the question is how to find this optimal policy and value function. One way is to repeatedly apply, as I just told you, Bellman operator, but it is a quite expensive process. So in that case, we can use this policy iteration or temporal difference methods, which is apart from these, a level up from this basic theorem. So today we are discussing till this point. Next slide, please. Hello? Hello? So what we discuss, let us not conclude this. Please stop this. Please hold this slide. I'll explain you since the start what we discussed today. We discussed the basics of functional analysis. Very basic first was metric space. What are metric spaces? Any set with a metric is known as a metric space, and that metric must satisfy four properties: identify, non-negativity, triangular inequality, and one more. What was that? What was that? Symmetry. So a metric which satisfies these four properties together with the set is known as a metric space. Then we discuss the complete metric space. What a complete metric space is? A metric space is said to be a complete space if every Cauchy sequence is convergent in that. And now the question is, what is a Cauchy sequence? Cauchy sequence is a sequence in which the distance between any two terms of the sequence is always less than a very small number epsilon, which is greater than 0, is known as a Cauchy sequence. So all the convergent sequences are Cauchy, but all the Cauchy sequences are not convergent. If a Cauchy sequence is convergent in a metric space, then it is known as a complete metric space. And then we discussed contraction mapping. What contraction mapping is, if we will consider the distance between the images of 2 points, then that is always less than the distance between the pre-images of these points. So such type of maps are called contraction. What they are doing is they are basically reducing the distance between the elements when we talk about those distances in domain, in codomain. So or we can say in range. So this becomes a contraction. And you know, whenever we apply a contraction again and again, like x to y, we are applying a contraction, distance has been reduced. From y to z, again we are applying a contraction, again the distance will reduce with the same amount. And again, if we are applying, the distance will reduce with the same amount. So in this way, what we can see at the end of the process, we will be left over with a single point, and that is known as a fixed point. So this is the way we are using this fixed point theorem, Banach fixed point theorem. Banach fixed point theorem with contraction map. Actually, it is a contraction map on Markov decision problem. So this was the application part of fixed point theory. What we did, we used fixed point theory in reinforcement learning problem by formulating the reinforcement learning problem into a Markov decision process. As the problem has been, if problem has been formulated in terms of stochastic process or the Markov decision process, then what the aim remains is to find out the optimal policy, and the optimal policy which maximizes the rewards. So you have in my slides, you can see the Bellman operator. Bellman operator is a contraction basically that we have proved in our slides. So what that contraction does is that contraction reduces the distance between the value function, and value functions are such that the rewards are maximized. So in this way, we can find a sequence of value function, and the sequence is a Cauchy sequence because every time B has been right, which is a contractor. So all these sequences, all these terms of sequences are value functions, and it is a contraction map. So the distance between any two value functions is always less than as and when we apply this Bellman operator. And this is a convergent sequence. Why? Because we are talking in R, L infinity. L infinity, R with L infinity is a complete metric space. So this Cauchy sequence will always converge at a point which also lies in this sequence, in the set. This means we will definitely get a policy which is optimal, where the rewards are maximized. So this is what was the aim of our talk today, to discuss the application of fixed point theorem and non-fixed point theorem in reinforcement learning. So now you can see when I start learning this machine learning, I thought there is no use of pure mathematics in machine learning. Moreover, we talk about linear algebra, we talk about probability theory, we talk about statistical analysis when we discuss machine learning problems. But now after this discussion, you will get a flavor of fixed point theory into machine learning. This is a base. Basically, fixed point theory is the base of machine learning. We cannot say that into machine learning, although I can give you few examples I have noted. Poisson processes are used in waiting time and queues problems, and this is a stochastic process. And one more is Brownian motion processes. These processes are used in trading algorithms, and all these are stochastic processes. These are already being used by different problems, algorithms in trading. And if we talk about Markov decision processes, then these are used in computational biology and reinforcement learning. So stochastic processes are already in use in waiting queue problem, in trading algorithms, in computational biology, and in machine learning. Basically, in reinforcement learning, Markov decision processes are used. So now onwards, you cannot say that machine learning is not using pure mathematics. What is a pure mathematics? If we talk about pure mathematics, we say fixed point theory, functional analysis, real analysis, and this is of no use. This has no practical use. And now you can see, I started my talk with basis of maths. I then machine learning, which involve many examples of real life situations. I can give many more examples of machine learning of real life situations. And then I concluded at the point where we discussed Bellman operator and its contraction and the completeness of the space, and then we concluded at fixed point theory. So now you can see that pure maths has its applications in real life problems also. The only thing is we need to find out, we need to explore the ways. So I can give you one more example, like we need to, whenever we open our Google and the Google search engine and we search for something, so we see there sometimes what happens, the scroll down button, it shows recommendation list, okay, the recommended system. You have seen after a particular search that was the first article you get is the most searched article, which got the maximum views. So the machine learning problem. Okay, if sometimes happens, a mail comes and it has already been transferred into span without your interaction. So it may be the case the mail will be having few words which are coming under the algorithm of spam mails. So we are spam, but these mails are automatically sent to spam folder by machine. So this is a machine learning problem. So, and like we discussed this bicycle example, this is reinforcement learning. So we can talk about many more examples in real life which comes under machine learning and classification task, regression task, or reinforcement learning problems. But if we will talk about Markov decision problems, so as far as I have explored till now, these processes, Markov decision processes are being used in reinforcement learning problems. It may be in supervised and unsupervised also, but as far as I explored till date, these are used in reinforcement learning problems where the RL agent means reinforcement learning agent is learning by itself with an interaction to the environment. And in such cases, what happens is when a particular RL agent is interacting with the environment and learning by trial and error policy, so he or she or an individual or anyone is learning through his or her experience, and the learning is being improved by a measure, and that measure by which the particular person is learning is known as performance measure, or we can say reward. So it is a numerical value. Every time that reward will increase so that the person may know his or her performance, whether it is improving or not, whether it is constant or it is improving. So our aim becomes now, since the process is random, it is a random process, we don't know what we are going to do. So the process is partially dependent and partially independent on the task performer, whosoever is performing the task. So the process is a random process. It depends on task performer. And the performance is measured by a reward, and our problem will always be to find to maximize the reward. And while maximizing these rewards, we will be taking a transition from S state to S1 to S2 to S3. And every time we enter into a space, we will be getting a value function. And that value function will use the previous experience of the previous stage. So this is what Bellman operator is doing. So with these words, I want to conclude that learning all these is a good way to enter into machine learning with fixed point theory. But this is the base. Not all, this is only the base knowledge. You need to explore more, and where you need to explore has been written in this second last slide. The areas to explore. Bellman optimality equation is the base vision of reinforcement learning. It is not the final, it is the start of fixed point theory into machine learning, into reinforcement learning. With these words, I would like to thank to all the listeners, and I would like to say sorry for all these internet glitches came in between. Thank you very much, Usha ma'am and Ramanand sir, for cooperating with me. Thank you so much. And if you have any queries, then it can be discussed either today or later on. You can discuss. You can have my mail ID. You can send me your queries. I'll be available. Thank you so much, ma'am.
Thank you so much, ma'am, for your excellent and informative presentation, ma'am. We are enlightened with your knowledge and presence. Thank you, ma'am. Our next session will begin at 4 p.m.
Thank you, ma'am. Shall I leave, ma'am?
Yes, ma'am.
கிளம்பிட்டாங்க 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 சார் சரி சரி சார்
Izharuddin sir, is it audible?
Yes, I'm here.
Izharuddin sir?
Yes, I am here.
Okay, sir.
Yeah,
Sir,
please.
welcome, sir. Welcome to our national conference, sir. Sir, is there any presentation to share? Sir, is there any presentation to share?
Yes, I am ready.
Formal welcoming, just we'll check once and then we'll go for formal welcoming, sir. We'll go into the session, sir. Sir, please try to share your PPTs so that once if it visible, once if you can confirm, then we'll go for formal welcoming and then formal process. Sir, in the bottom
So
you
do
can
you
see
need my PPT?
Share option. இல்ல சார் நான் ஷேர் பண்ணல சார் yes sir.
Yes,
Now it is
please.
visible, sir. Yes, sir. You can go with hide and then you can go for full presentation, sir.
Can I start?
Okay, sir. Sir, but your voice is a little low, sir. Too low.
Okay, so I'm doing. Wait a minute. Now?
Sir, please check
Now
for
my voice
increase
is
of
coming?
volume.
Now my voice
Yes,
is
sir.
coming?
Face, sir. Your face. A little bit you have to lower your screen
Okay.
camera. Yes,
Yeah,
sir.
I will speak loudly. Then
Yes.
you will allow me.
Yes, sir.
Okay, yes.
So welcome, sir. Welcome back to day 1 afternoon session for Invited Talk 4 for UGC sponsored National Conference on Analysis and its Applications focused on Fixed Point Theory NCAAFFPT 2021. So which is going to be held, which is holding on 2 days, 24 and 25th. So for our day 1 afternoon, that's the last session for an invited talk. So it's my pleasure to welcome Dr. Izharuddin on behalf of the entire management of DG VAISHNAV College, on behalf of our secretary Ashok Mundraji, on behalf of our beloved dynamic principal Dr. Santosh Babu, and the convener of this program, leader of this mathematics ship, Professor R. Venkatramanan. So on behalf of the entire team of this mathematics PG and research mathematics department, so it's my immense pleasure to welcome Izharuddin for this conference, sir. So I welcome you, sir. So Dr. Izharuddin is working as an assistant professor at the Department of Mathematics, Jamia Millia Islamia University, New Delhi, since 2015. Dr. Izharuddin has completed his PhD from the Department of Mathematics, Aligarh Muslim University, Aligarh, in the field of non-linear function analysis. During his PhD, he worked on some problems of approximating fixed points in VAISHNAV as well as CAD O spaces. He has published more than 30 research papers in international journals of repute with high impact factor like fixed point theory applications of impact factor 2.49, Journal of Nonlinear and Convex Analysis of impact factor 0.9, Bulletin of Malaysian Mathematical Sciences Society impact factor of 0.854, and then Mediterranean Journal of Mathematics of impact factor 0.8, and then Revista Dali Real Academy di Ciencia Exacta of impact factor 0.69, and many others, just to mention a few. Dr. Izaruddin has been presented. He presented more than 31 international and conferences, international national conferences, which held in India and abroad, which includes USA, Thailand, Taiwan, and Turkey. Moreover, he has extended 8 workshops and advanced training program. Dr. Izaruddin has qualified CSR UTNet exam in June 2009 with All India ranking of 58 and awarded Maulana Azad National Fellowship by UGC during his PhD. Also, he has been worked as an assistant professor ad hoc for 4 months in Applied Science section, University Polytechnic, Aligarh Muslim University, Aligarh. I welcome you, sir. More than his as an achievement, he availed Maulana Azad National Fellowship during his PhD. He is a qualified net holder. And then from IMRF, Best Scientist Award at the Caramel College of Bellman, Nuwan, Goa on December 2018. And then Young Scientist Best Paper Presentation Award in 17th Annual Conference of VPI at the GTP College, Rajnath Govan, Chhattisgarh, India on February 2021-2015. And he got a Best Oral Presentation in SESFC 2014 at HSCA. So I welcome you, sir. Welcome you for your valuable talk. I welcome you, sir. On behalf of the entire Maths Department, PG Research and Department of Mathematics, I welcome you, sir. So now I hand over this session to you. Welcome, sir. So now you can unmute and then you can go for presentation, sir.
Yeah. Thank you very much for your nice and lengthy introduction. I think I'm not deserving for such a long introduction because I'm considering myself as a learner. So first of all, I want to thanks all the entire organizing committee who are working behind or from the front for this national conference. Okay, on analysis and application is focused on fixed point theory and application. So,
sir.
Yes, my voice is coming.
Yes, you are audible, sir. But you can go for your screen sharing for PPT, sir.
Okay, yeah.
Yes, sir. Now it's visible, sir.
And,
sir, you can press F5, sir.
Okay, yeah. And second thing, I want to.
Yes, sir. Press F5, sir. Will come for full screen, sir.
Yeah. I sincerely apologize being delayed because of some.
Yes, sir. Yes, sir.
In jam, so that's why I cannot reach within time. So this is the title of my talk, some recent fixed point theorem for monotone mappings. So before coming to the particular topic or particular problem of fixed point theorem for monotone mappings, I want to recall some basics. I believe that a lot of things has been said about by Professor Marodai, Professor Alfred, and Dr. Aarti Saxena regarding the fixed point. But again, because I want to say something from my side, so I want to start again basic notion of fixed point. By my point of view. So in my view, what is the fixed point? So there are two things are involved. If you see here, number one, a non-empty set. Number two, a mapping T. So there are two things. Number one, underlying map, or you can say underlying set X. Number two, underlying mapping T. And a point X belongs to X is called the fixed point of a mapping T if it satisfies Tx equals to X. So if it satisfies Tx equals to X, we say that X is a fixed point. And Ft denote the collection of fixed point of a mapping T. So these are some examples, very easy examples. If X is the real line, if we take Tx equals to 2X, so by easy calculation, we can see that T have only one fixed point. By example 2, if we define Tx equals to like this, so we can see that T has two fixed points. If we define simple translation by as Tx equals to X plus A, so we can see that there is no fixed point. If we have identity map, so we can see that it has infinitely many fixed points. So by these examples, which are very simple but very informative, what information we can exert from these examples? In general, a map may have a unique fixed point, may have more than one fixed point, may not have a fixed point, may have infinitely many fixed points. So, and another thing is that geometrical meaning, I believe that people have been recalled that. What is the geometrical meaning of fixed point? It is nothing but the intersection of line y equals to x and the curve y equals to tx or fx. So intersection of the line y equals to x and intersection of curve y equals to fx is nothing but the fixed point of mapping. What is the meaning of a fixed point theorem? So as I recall that there are two things are involved. One is underlying mapping T, another is underlying set X. So by a fixed point theorem, we mean a statement which assert that under what suitable condition a mapping T defined on a set X admits a fixed point. So what is the meaning or simple way? A fixed point theorem is nothing but the union of conditions which are being put on underlying mapping T or underlying set X. So, and these are the very basic fundamental things. There are three very fundamental fixed point theorems, or very basic discovery in the fixed point theory. One can see that on the basis of these pillars of fixed point theorems are three basic theorem of fixed point. We can divide fixed point theory in entire different section. One is called algebraic fixed point theory. Some people used to call discrete fixed point theory. And one of the basic theorem in this section is nothing but the Terrestrial fixed point theorem. And the statement is really simple. Every order preserving mapping defined on a complete lattice has a fixed point. Every order preserving mapping defined on a complete lattice has a fixed point. This is one of the basic theorem of this section of fixed point theory, which is called discrete fixed point theory or algebraic fixed point theory. Another important theorem or basic fixed point theorem is Brouwer fixed point theorem, and it's give the direction to the fixed point theory as topological fixed point theory, or you can see the topological expert of the fixed point theory. Again, you can see that statement is really simple. Again, any continuous mapping defined on closed unit ball of Rn has a fixed point. So I want to say two things about this very basic theorem. This is the Brouwer fixed point theorem, and very old one, very basic one. But if I recall that if n equals to 1, so you can see the closed unit ball of our real line. So if n equals to 1, so if we work on the real line, so what we can observe that closed unit ball, we can convert it into the closed interval. Any continuous map defined on closed interval of real line has a fixed point. And this is one of the very basic exercise just after the intermediate value theorem in any BSc course, in any real analysis course in undergraduate level. So this is such a basic theorem, but when we go in the higher dimension, proofs are really interesting. And there is very interesting article written by Professor Shepard from South Korea. He wrote an article, 70 years of Brouwer fixed point theorem. 70 years of Brouwer fixed point theorem. A lot of proofs of the fixed point Brouwer fixed point theorem has been given. And another very recently by a Thai mathematician, Professor Sompong Dompongsa. Professor Sompong Dompongsa has given a simple proof of Brouwer fixed point theorem, and the proof is only the paper has been published in Thai Journal of Mathematics and Thai Journal of Mathematics, and it is written by Professor Sompong Bongsa. So I urge or I request to the learner of the fixed point theory who are working in the fixed point theory or who are willing to learn fixed point theory, please try to see the proof of this very basic theorem. And also that, because this is a finite dimension, one can say, because it's Rn. So this very interesting theorem cannot be extended to infinite dimensional. So after having a counter example, a contradictory example, Teknoff has given very interesting variant of infinite dimension version of Brouwer fixed point theorem. So people must see some proof of Brouwer fixed point theorems, which can involve the background of some algebraic topological concept, some concept of a different variant of degree theory and all. So, but very interesting proofs. Many proofs are, so we must see that. Okay, so another branch of fixed point theory are not only me, but if I say that it is one of the most popular branch of the fixed point theory, so there should not be any contention. And people used to call as metric fixed point theory or analytical fixed point theory. And one of the basic fixed point theorem, or if I say that it is one of the most famous fixed point theorem, not only the most famous fixed point theorem, but it is one of the most fundamental result proof in mathematics ever proof. So one is really basic proof of that. What is that? Statement is really interesting. As I said that there are two things are involved. Number one, underlying mapping. Number two, underlying set. So again, you can see that what we are doing, we are putting the condition on underlying mapping. So in Banach contraction, it has to be contraction mapping. So what we are doing, we are putting the condition on underlying mapping T. Our mapping has to be contraction. What is the meaning of contraction? Suppose X is a metric space, T is a mapping from X to X. So the distance between the image D of Tx comma Ty must be less than K times D of Xy, where this K lying between 0, 1 cannot be 1. So this is called the contraction. So we are putting the condition on underlying mapping T. Not only this, we are putting the condition on underlying space. Hello? Yeah? Sorry, someone has called me. So what we are doing, we are putting the condition on underlying space also. We are putting the condition on underlying space. Our space has to be complete metric space. And everyone knows that what is complete metric space? In which metric space every Cauchy sequence is convergent. Every Cauchy sequence is convergent. One of the very basic example, real line with respect to usual metric is complete. Space of all continuous function with supremum metric is complete. LP spaces, classical sequence spaces, function spaces, these are some examples of complete metric space. So the class of a complete metric space is interesting class. So any contraction map defined on a complete metric space has a unique fixed point. Okay, so one interesting thing is that, so in this Banach contraction, there are two terms. We are putting some condition on underlying mapping T, and we are putting condition on underlying space. So now if we want to go beyond this theorem, so we have two things. Number one, either we can relax the condition on underlying mapping, or we can relax some condition on underlying metric space. Underlying metric space. My voice is coming or not? Hello? Professor, my voice is coming?
Yes, sir. It's clear,
Hello?
sir. Yes, sir. It's clear, sir. You can proceed.
Okay. Okay, yeah.
It's clear, sir.
So now one can see that there are two things. One is contraction mapping. Another is underlying metric structure, which is complete metric. complete metric space. So if we want to enlarge or we want to generalize these theorems, so we can do either we can weak the condition on underlying mapping, so that we can have more generalized class of the functions, or we can play with some structure of this one. So there are progress in both the direction. Generalization of Banach contraction theorem via weakening the contraction condition. So, and there are some famous. I used to recall the name of Byrne and Wong. What these Byrne, Wong, Kannan, Reich, Chatterjee, Zamarfescu, Girati, Sirik, Matkowski, Albert, Jalili, Karpinar, Ree, and there is many. I have missed Mir-Keller contraction, F contraction, Samit, sci-fi contraction due to Samit. What these people are doing, these people are weakening the contraction condition and putting underlying domain as a complete metric space. This is the one aspect. This is the one aspect of the research of the fixed point theory, that we can generalize the involving contraction mapping. Another direction of the research is that we can generalize the metric structure. One very interesting thing is that X is a metric space. So what is this? X is a non-empty set. D is a map from X cross X to R, such that D of xy is positive. Number one, dxy is positive. Number two, dxy is 0 if and only if x equals to y. Number third, d of xy equals to d of yx. It is called symmetric property. Number fourth, one of the most important properties is that d of xy is nothing but d of xz plus d of zy. This is called the triangular inequality. So the group of this condition is nothing but metric on set X. If we relax any condition or if we remove any condition, so a lot of impact of analysis. For example, if we remove triangular inequality, so a lot of result can be failed. For example, in metric space, the limit of a convergence sequence is unique. And to prove this, we use triangular inequality. How we use triangular inequality? Suppose xn is a sequence which is converging to x as well as y. So d of xy, if we start d of xy, by triangular inequality we can insert xn. So it will be d of x comma xn plus d of xn comma y. And xn is converging to x and y both, so it will tend to 0. So dxy is tending to 0 means dxy has to be 0. dxy is 0 by virtue of the metric x equals to 1. So now we are using not only triangular inequality, but we are using dxy is 0 implying x equals to y. If we remove either of the condition, either triangular inequality, either dxy equals to 0 implying x equals to y, we cannot prove this. In a metric space, limit of a convergence sequence is unique. So we have to be very careful. Why we are changing or why while we are relaxing any of the condition of the metric, all analysis may be changed. So lot of some attempts has been made in this direction due to Professor Bakhtin, B.C. Dage, Sarzwick, B metric space, D metric space, G metric space. Matthews introduced partial metric space. Some people work in fuzzy metric space. Mustafa and Sims, new approach to generalized metric space. And Huang and Zhang, cone metric space. Amin Harandi and some other people, metric like partial metric and fixed point. And very recently in 2019, with my co-author Asim and with my PhD guide, we introduced a new notion of generalized metric space, and we gave the name as MV metric space. MV metric space in Journal of Inequalities and Application in 2019. In this paper, what we did, we relaxed some condition on of metric space, we generalized underlying metric space, and we prove Banach contraction principle. Not only we prove Banach contraction principle, but we applied that very theorem to ensure the existence of initial value problem as well as integral equations. And very recently, one of my co-author from Thailand and from Dehradun, we proved Karasti fixed point theorem. Karasti fixed point theorem is also very basic fixed point theorem. Karasti fixed point theorem in MV metric space. So now, if anyone is willing, so anyone can try Mir-Keller contraction, anyone can try Boyd and Wong contraction, anyone can try Chatterjee contraction in this MV metric space. All the classical theorem we can try to extend in this MV metric space because very new structure, and we can have different direction of application also. So this is one point I want to share. This is very new structure, MV metric space in 2000. Only I could not saw any other paper except I did with one of my group of students and colleague, Karasti fixed point theorem, MV metric space, discrete dynamical system, which is also an SCI journal. I will share in the end if someone is willing. So if anyone is willing to do research, so those people can try basic fixed point theorem in MV metric space. So this is one interesting. Another interesting direction of the fixed point theory is that, what is this? Suppose X equals to R. R is, everyone knows that R is a complete metric space. And if we define a mapping Tx equals to X plus 3, this is non-expansive mapping. Non-expansive mapping is what is d of Tx comma Ty is less than d of Xy. The class of a non-expansive mapping is much bigger than the class of contraction mapping. But we see that Banach contraction theorem does not hold in respect of a non-expansive mapping, because you see that X equals to R, R is a complete metric space. But if we take non-expansive mapping, we don't have a fixed point. So there is a need to prove fixed point theorem with respect to non-expansive mapping, which is more natural than the contraction mapping. And these are the classical theorem, very classical theorem. Whenever I again request, if someone is doing research in the fixed point theory, please try to see the proof of these classical theorem. One is due to Professor Browder and one is due to Professor William R. Kirk, very basic, and both appeared in 1965. And so and people used to say Gode in the same year produce, but Gode proved that theorem in German. So I could not see ever the exact version of the Gode, but the statement is really exciting. What is that? K be a non-empty bounded closed subset of a uniformly Banach space. Now we have to understand uniformly convex Banach space. So any non-expansive mapping will have a fixed point. What the Kirk proved that K be a weakly compact and convex subset of a Banach space, which has a normal structure. So now we have to understand what is the meaning of a normal structure. And again, what is the relationship between weakly compact and bounded closed set or bounded convex set, so that we can compare which is more general. Theorem of the Browder is more general or theorem of the Kirk is more general. And here, but interesting thing is that Browder worked for uniformly Banach space, convex Banach space. The Professor Kirk took arbitrary Banach space. But Professor Browder took bounded and closed, but Professor Kirk took weakly compact. So what is the relationship between weakly compact and convex and closed bounded and convex? Why we are putting the condition of a normal structure? Very interesting. And the idea of the proof is really interesting. Idea of the proof is really interesting. What is the idea? What is the essential idea of the proof here? Very constructive. Very constructive. I can recall 2 or 3 lines. Collect the family of, suppose F is a family. F is a family of invariant set under the T. What is the family? Family is the subset of a, which are the subset which are invariant under the action of the mapping T. After that, define a partial ordering. The natural partial ordering is A is less than or equals to B if and only if B is less than A. B is subset of A, reverse partial ordering. So then construct a chain and try to show that this chain has an upper bound. So by use of the Jones lemma, if every chain has an upper bound, in a partial order set, then it will have a maximal element. So we can have a maximal element and try to show that that maximal element is a singleton. So proof is really interesting by use of a normal structure, and proof is really interesting. So again, I request those people who are working in fixed point theory, please try to see the proof of this. Very small paper of the CAT, 2 pages or 2.5 pages and 3.5 pages of Browder. But the idea is really exciting. What the idea is this: they are confining themselves to the non-expansive mapping, and they are looking the different variant or different geometrical properties of Banach space so that non-expansive map may have a fixed point. So it leads to very interesting branch of the fixed point theory, where geometric properties of Banach space play crucial role, very crucial role. We can have other property, normalized structure, OPL property, uniformly normalized structure, or many other geometrical variants we can utilize to characterize those Banach space which can have fixed point with respect to non-expansive. Very interesting, and most of the paper appeared in very classical journal. So this is a very interesting. Okay, another interesting observation. While working with the Banach contraction theorem, we can see that Picard sequence of Picard iteration generated by arbitrary choice of the point of underlying complete metric space. If T is contraction, it will converge to fixed point. It's always fixed point. But take x equals to minus n1, it is close. So being the closed subset of complete metric space R, it's self-complete. If we define a map Tx equals to 1 minus x, so you can also that T half equals to half. This is the half is a fixed point. But if we associate Picard iteration, so it need not be converted to the fixed point. If we suppose x naught is 1 by 3, so by Picard iteration, x1 is Tx naught, it will be 2 by 3. X2 is Tx1, it is 1 by 3. X3 is 2x2, which is 1 by 3. So it is an oscillating sequence. So we can see that this is a non-expansive mapping. Underlying space is a complete metric space, and it has a fixed point. Even Picard iteration does not converge to that fixed point. So what we do, we need to approximate the fixed point of a non-expansive mapping. We need to construct some iteration process which can converge to the fixed point. So in this way, we can have this iteration process. There are 3 basic iteration process: Mann iteration process, Ishikawa iteration process, and another is Halpern. But again, you can see that here we need this addition operation, this is scalar multiplication operation. So this study of Mann iteration as well as Ishikawa iteration, we cannot make these study in the setting of a metric space, because there we don't have scalar multiplication, where we don't have addition, so we cannot study. So again, to study the approximating fixed point of a non-expansive mapping, either we can confine our study to Banach space or Hilbert space. We cannot study as it is these iteration processes in metric space. And there are very interesting list of iteration process. Noor iteration process, very famous. And after this paper in 2007, R.P. Agarwal, Donian Reagan, D.R. Sahu, Professor Sahu will speak tomorrow. Everyone must listen his talk. Dr. Javed Ali will speak tomorrow something about iteration process also. Very interesting talk. He is my senior colleague. I have learned a lot of things from him also. And Professor Sahu is always a man of inspiration for all of us who are working in an approximating fixed point in Banach space. So after this iteration, which appeared in Journal of Nonlinear Convex Analysis, lots of people work on iteration process, and they compare the rate of convergence. A lot of people, Gursai or Karakayar, D. Thakur stand for Deepti Thakur, B.S. Thakur, Balwant Singh Thakur. Professor Balwant Singh Thakur is also very strong researcher in the area of approximating fixed point in Banach space. He is a very generous professor in Pandit Ravi Shankar Shukla University. He is very helpful. He proved these two. In Applied Mathematics and Computation, very strong journal. Flomet, very strong journal. And in Applied Mathematics Computation, he introduced a new iteration scheme for approximating fixed point of Suzuki generalized non-expansive mapping. And in Flomet, he introduced a new iteration scheme for approximating fixed point of a non-expansive mapping. And with the help of example, he proved that his iteration converge faster than the others. Kifayatullah and Ershad produced another iteration scheme. Very recently, with my student Chanchal Goredia, we also introduced a new iteration method. We also constructed an example which shows that our iteration process converges faster than the others. And we also applied that very construction process in solving feasibility problem, which is a very interesting, which includes some variation equality problem and complementary problem and some other problems. Now, I want to say something about this very interesting generalization of Banach contraction theorem. If you see that, I am recalling, this is the contraction condition, d of dx comma y is less than k times dxy for all x and y in x. But if we impose ordering on metric space, what is that? X d be a complete metric space endowed with a partial order. And we are checking this contraction condition only for those x and y which are comparable. Means we are not checking our contraction condition for all x and y in x as we checked in Banach contraction theorem, but we are verifying our contraction condition only for those x and y which are comparable with respect to the given partial order. And with addition supposition, if there exists x naught which is comparable with this image, then it has a fixed point. This is one of the very basic result in 2004 proved by Rainer Rohring, and they applied this result to prove matrix equations. system of matrix equations. And after 1 year, Professor Newton, I don't have any contention whose paper come earlier, communicated one, almost same results, but Newton and Lopez applied their result to the periodic differential equation, and they prove existence of solution of periodic differential equation. And after that, I am skipping this because of time constraint. I'm showing. Okay, so now after that, monotone. What is the meaning monotone? If x and y are comparable, or if x is less than y, then tx must be less than ty. This is the meaning of the monotone. Renner and Newton and Lopez has done with respect to monotone contraction, and some other people for generalized contraction also did. Now, what can happen with respect to non-expansive mapping? Monotone non-expansive, what will happen? So there are some people did something. Bashar and Khamsi, Abdul Latif et al., Song and et al. Prove some monotone non-expansive mapping. Dashish and Khamsi proved weak convergence of Mann iteration for monotone non-expansive. Song et al. Consider weak convergence of Mann iteration for monotone non-expansive under some different condition, in contrast to Dashish and Khamsi. And Busana bin Dashish proved Brother theorem for monotone non-expansive mapping. And very recently, with my student Chanchal Gureria, we did a study of monotone non-expansive mapping in setting of a cat-zero space, which is non-trivial, non-linear. We proved very interesting. We plot some graph. We provided some application. Now I can show you some of recent progress. With my student Chanchal Guloria and Professor John Jos Nieto, we have studied Mann iteration for monotone non-expansive mapping in order cat-zero space. What is the speciality and what is the highlight of this paper? We studied Mann iteration in the setting of a cat-zero space. As I recall, we cannot study Mann iteration in metric space. Why? Because of lack of convexity structure, because of lack of linear structure, because of lack of scalar multiplication and usual addition. So it is always a good question to extend result of a linear space to non-linear space. So how we can prove that? How we can study Mann iteration in a non-linear space? So for that we choose cat-zero space. Very special type of convexity structure is there. So in this paper we studied Mann iteration process with respect to monotone non-expansive mapping in ordered cat-zero space, which is a non-linear space. And also we constructed some examples. Also we provided application to integral equation. In 2018 we published this paper. Now after that, very interesting paper with my student Sajan Agarwal and again Professor John Jos Nieto, a fixed point theorem for monotone nearly asymptotically non-expansive. And very strong journal of fixed point theory and application, one of the best journal of our field. In this paper, what we did, basically we did, we studied monotone nearly asymptotically non-expansive mapping. But again, we proved the existence in the setting of hyperbolic space, hyperbolic order metric space, which is again a non-linear space. Again, with my student Sajan Agarwal, I studied convergence and stability of Fibonacci-Mann iteration for monotone non-linear mapping in Demonstration Mathematica, again in the setting of hyperbolic space, which is again a non-linear space. Again, with my student Sajan Agarwal and with Professor Poom Kumam of the Thailand, we prove some convergence theorems in hyperbolic metric spaces again, which is again a non-linear space. again for monotone non-expansive mapping. So these are some highlights of with respect to monotone non-expansive. These are the recent research with my students all this, and very recently from monotone we progress to graphical version of fixed point theory. Jashmeshki proof bana contraction principle indoned with graph, and after that there are few pupils who were graphical version of non-expansive mapping. Khamsi is one of the pioneer men, Al-Fradin is one of the pioneer men, and we also did with my student Sabia Khatun. I proved some iteration process with respect to G non-expansive mapping. So now from monotone non-expansive mapping, we are transforming ourselves to G non-expansive mapping, and we are trying to do some application to signal processing and other. So it's very interesting. Part of that, I am working very hard with my student Sabia Khatun for applying G non-expansive mapping, and we are trying to applying these approximating fixed point results to the image processing. We are developing image with respect to some iteration process, and our study is in process. And this is the paper with my friend Asim and my guide in that. And there are some interesting results with my student Chanchal Guleria, new iteration method. And this is very interesting. Some convergence theorem and involving new iteration scheme with my senior Dr. Javed Ali and Professor Vladimir Rakovich. So these are the sampling. And very recently, I'm showing, please don't wait a minute. Very I want to show two recent paper. I want to show recent paper. One is due to this. So I'm showing this paper. Please see this paper. A novel approach to the solution of boundary value problem via green function and fixed point iteration. This is with my senior Dr. Javed Ali and with my researcher Fahim Ali. In this paper, what we did, we used Picard as iteration, and we used this iteration to approximate the solution of boundary value problem. Very recent, in 2020, it is published. We did this paper, very good results. And another interesting result, which I want to show. This approximating fixed point and its application to fractional differential equation. In this paper, we use L for Reich Suzuki generalized non-expansive mapping, and we use some iteration process, and we applied this study to approximate the solution of fractional order differential equation, which is nowadays a very hot topic, because lots of real life problem cannot be expressed properly in terms of ordinary differential equation. They need to express in terms of fractional differential equation. So we applied this fixed point theory to existence and approximating solution of fractional differential equation very recently. This, and I want to show you one more paper, which I said earlier. Okay, title of this paper, you can see Convergence Analysis of Modified Bass Iteration for 2G non-expansive mapping. So in this paper, What we did, we are transformed ourselves from mono non-expansive to G non-expansive mapping, and we convergence analysis of that. But while studying approximating fixed point, or while studying any iteration process, so we need to focus on computational cost also, computation time also, number of iteration also. And very recently, there is a one approach to compare the rate of convergence due to Brande. But many researchers, many professors are pointing that very particular approach is not the perfect. So we have to be very careful while claiming that our iteration process is best or our iteration process converging fast. We have to be very careful. So with these some highlight, I am stopping myself, and I am welcoming questions. So please ask the questions. Thank you very much for your kind attention and your kind time.
Thank you, sir. Thank you, sir. Sir, actually, question it came from Om Prakash Gange.
Yes.
Any latest publications on applications on fixed point theorem? I think that is what you have shown. Better you can explain again. Any latest publications on applications on fixed point theorem?
Latest application. Asian option as a fixed point. Asian option as a fixed point. So you can write Asian option as a fixed point. What is Asian option? Asian option as a any latest publication on application of fixed point theorem. So you can see Asian option as a fixed point. So in this article, what one professor did, it's a journal of fixed point theory application. Asian option is a process to fix the price of a share, and professor utilized Banach contraction principle. Okay, how we can so it is one. And very recently you can see the paper of Professor Kumar. He has done a lot of application in signal processing, a lot of application in image debugging, a lot of application in economics also. You can see that in optimization theory. So a lot of papers are appearing in this direction.
Thank you, sir.
Other question, please.
So it's our personal goal. Suppose if one wants to start with there is a fixed point theorem, where he can start, how we can proceed.
For research point of view or something?
Yes, research point of view. In research point of view.
Okay, so my advice is that first of all, read one good book. There are some good books. You can read book of Gokul and Kerr. You can read book of Khamsi and Kerr. You can start reading those basic fixed point theorems. As I said, there are few directions. One is that enlarging the contraction condition, so you can go in that direction, or you can generalize involving matrix structure. You can go in that direction, and you can have some application point of view. You can have application in integral equation. You can have application in boundary value problem. You can have application in fractional differential equation. You can have application in optimization problem. So you can go in that direction also. Another direction is if you want to go for the non-expansive mapping iteration process, so you can follow Professor D.R. Sahu book, very good book. You can read that book. Professor Bessel Berende book, you can read book. So a lot of so you can choose one direction and try to go deep in that direction. If you need my help, I can share my details with Professor. So anyone can ask any query to me. I have shared. So this thing, anytime. It may happen that I cannot pick call or I cannot. So, but I will respond surely later.
Okay, sir.
Yeah. So any other questions or query?
Sir, As you mentioned, we can find its application in signal processing, image processing.
Yes.
Is there any part of speaking this with information security, information in that sense? Is there any possibilities there?
I did not explore exactly because I am
Okay.
still studying. What my motivation is that, for example, your picture. So
Ah,
what I will try to do, I will try to make you more smart. If your picture is blurred, if your picture is not very bright or it is diminishing, so what we are doing, we are trying to applying fixed point iteration to magnifying that to uh, image should not be blurred, it should be bright. So we are trying to do that, we are trying to study that.
okay. Sir, one more question is from the audience.
Yeah, please,
They're
please
asking
ask.
for they're asking for request one basic book on fixed point theorem.
I said there is a one book of Dr. Sahu, Professor Sahu book, one book of
Yes.
uh, yeah, Kark and Khamsi. This is very basic books, must see.
Okay.
Yeah. Okay.
Thank
Yes.
you, sir.
What question?
I hope so.
I
The
I am
final.
really sorry. I am really sorry I was late because of some jam and traffic. So I sincerely apologize again, and I am very much thankful for your college to inviting me. I am very glad to see all of you, and I will be more happy if either you come to my university or I can visit your college live. I want to discuss. We can have some joint project and all other things. It will be very good for our college and my university also.
Excellent,
Thank you
sir.
very much. Yeah.
Yes, sir. Excellent, sir. So thank you, sir. Thank you for your wonderful, informative talk on some recent points, some recent fixed point theorems for monotone mapping. Hope so. You have covered, I think, almost 15 to 20 years. I was seeing you have covered around 20 years recent papers, article, and also. How about analytic and metric fixed point theory, generalization of Banach contraction theorem, and then how we worked on MV metric spaces. Even you have given open problem on that. One can work on the open problem on MV metric space and the iteration
Yes.
process. How monotone can be now, how it has been imaged to graphical version. It was wonderful, sir. Thank you, sir. Thanks a lot. On behalf of the entire the management of DG Vaishnav, it's a special thank for you. And then on behalf of the entire team of Mathematics Department, PG Research and Department of Mathematics, I thank you, sir, personally. And then on behalf of the entire team, sir. Thank you, sir. Thanks a lot. Thank you.
Okay.